Timeless Concepts from Physics Helpline. This is a video tutorial series through which we will sharpen our problem-solving skill. First, we will analyze the problem on hand to find the related concepts. Then, using these, we will develop a method which will produce the solution. This will help the students aspiring to get into IIT to understand the much needed advanced theories and applications in physics. In this video tutorial, we will discuss 3 multiple choice questions in rotational motion of rigid bodies. The questions are as follows. Question 1. A thick hollow sphere having outer radius r rolls down a rough inclined plane without slipping and reaches the bottom with speed v. When the sphere is released on a smooth inclined plane of identical shape, it reaches the bottom with speed 1.25 v. Then the radius of gyration of the sphere about its diameter is. The options are 0.4 r, 0.5 r, 0.6 r and 0.75 r. Question 2. A thin uniform rod of mass m and length l is at rest on a smooth horizontal surface. An impulse J is applied at one end of the rod perpendicular to its length. Then the time taken by the rod to turn through a right angle is. The options are 2 pi ml divided by J, 2 pi J divided by ml, pi ml divided by 12J and pi J divided by ml. Question 3. A uniform circular ring of mass m is placed on a rough horizontal surface. An impulse J is applied to it in the plane of the ring through its center and parallel to the surface. Then the linear velocity of the center of mass of the ring when it starts pure rolling is. The options are J by m, J by 2m, J by 3m and J by 4m. First, let us solve the problem in question 1. The situation is shown in the figure. The figure shows a rough inclined plane of height AB is equal to h. A thick hollow sphere is placed at the top of the inclined plane at A. We are required to find the radius of gyration of the body about its diameter. When released, it rolls down without slipping and reaches the bottom of the inclined plane C with velocity of center of mass v. In pure rolling motion, velocity of center of mass v and angular velocity omega are related as omega is equal to v by r, where r is the outer radius of the sphere. If mass of the body is equal to m and radius of gyration is equal to k, then moment of inertia of the sphere about its diameter is I is equal to mk square. We are required to find the value of k. We will use the kinetic energies of translation and rotation and total kinetic energy to evaluate k. In the first case, the inclined plane is rough. Therefore, the motion is both translation and rotation. In the second case, the inclined plane is smooth, therefore motion is only translation, since rotation is not possible without friction. Now let us calculate the kinetic energies in the two cases. In the first case, kinetic energy of translation is equal to half mv square. Kinetic energy of rotation is equal to half I omega square, which is equal to half mk square into v square by r square, which is equal to half mv square into k square by r square. Therefore, total kinetic energy is equal to half mv square into 1 plus k square by r square. In the second case, total kinetic energy is equal to kinetic energy of translation only. Now, velocity of the sphere at the bottom is equal to 1.25 into v, which is equal to 5 by 4 into v. Therefore, total kinetic energy is equal to half m into 5 by 4 into v whole square, which is equal to half mv square into 25 by 16. Now, in both the cases, decrease in height is equal to h. Therefore, loss in potential energy is equal to mgh. Therefore, total kinetic energy at the bottom are equal in both the cases. Therefore, we have half mv square into 1 plus k square by r square is equal to half mv square into 25 by 16. This implies 1 plus k square by r square is equal to 25 by 16. Therefore, k square by r square is equal to 9 by 16, which implies k by r is equal to 3 by 4, which is equal to 0.75, or k is equal to 0.75 r. Therefore, the correct option is D, which is the answer to question 1. Now we will solve the problem in question 2. The situation is shown in the figure. Length of the rod AB is equal to L. It is placed on a smooth horizontal surface. Mass of the rod is equal to m. The impulse applied to it at B is equal to J. The rod is free to rotate on the surface. Therefore, it will rotate about the central axis perpendicular to its length. Therefore, initial angular momentum of the system about the axis is L1 is equal to JL by 2. After the impact, let the angular velocity of the rod is equal to omega. Moment of inertia of the rod about the central axis is equal to 1 by 12 into ml square. Therefore, final angular momentum about the axis is L2 is equal to I omega, which is equal to 1 by 12 into ml square omega. We observe that the net external torque acting on the system is equal to 0. Therefore, angular momentum of the system is conserved. Therefore, we have 1 by 12 into ml square omega is equal to JL by 2. On simplification, this gives omega is equal to 6J by ml. Now, the angle described by the rod in time t is given by theta is equal to omega t. It is given that theta is equal to pi by 2. Therefore, we have omega t is equal to pi by 2 or t is equal to pi by 2 omega. Putting the value of omega and simplifying, we get t is equal to pi ml divided by 12J. Therefore, the correct option is C, which is the answer to question 2. Finally, we will solve the problem in question 3. The situation is shown in the figure. Mass of the ring is equal to m and radius is equal to r. It is placed on a rough horizontal surface. Impulse applied on the ring is equal to J. It is applied along the horizontal line passing through the center of the ring. It is given that the ring executes pure rolling motion after the impact. Let the uniform velocity of center of mass is equal to v and uniform angular velocity is equal to omega. Therefore, we have omega is equal to v by r. Now, initial angular momentum of the system about the point of contact is L1 is equal to J into r, and final angular momentum about the point of contact is equal to angular momentum of the ring about the center of mass due to rotation plus angular momentum of the center of mass about the point of contact due to translation. Therefore, we have L2 is equal to I omega plus mvr. Now, moment of inertia of the ring about the center of mass is I is equal to mr square. Therefore, L2 is equal to mr square into v by r plus mvr. On simplification, this gives L2 is equal to 2 mvr. Now, the net external torque on the system is equal to 0. Therefore, angular momentum of the system is conserved. Therefore, we have L1 is equal to L2. This implies 2 mvr is equal to jr or v is equal to j by 2m. Therefore, the correct option is B, which is the answer to question 3. This completes the answers to the questions.